Hi everyone. Today we will be going through the week 5 homework problems. So before we begin, previously, I used to have some learning objectives. So what we will learn through this recitation class. So one of the thing we will learn about is water hammer system. So we will know how to calculate wave celerity and pressure head rise for rapid valve closure and predict whether how changing in fluid density or pipe flexibility will affect the severity of water hammer. And I will also define water hammer phenomena, and we will go through the problems related to pump power and efficiency, where we will apply motor, pump, and combined efficiency accurately through the power cascade. We will use this formula for solving the flow rate, pump head, and power output as well. And we will also utilize the energy equation. Before we jump into numericals, so let us understand few formula. So for a rapid closure valve, where time is less than 2L by C, this is celerity. This pressure head rise caused by water hammer will be equal to initial velocity times C by G, where C is wave speed, which will be equal to EC by rho. EC is a composite modulus of elasticity of water pipe system, whereas rho is density of water. Similarly, this will be EC will be composite modulus of elasticity of water system will be equal to 1 by modulus elasticity of water plus dk by EP times E. So E is thickness of pipe walls, EP is modulus elasticity of pipe, K is constant. So in our numericals, we will utilize all these formula. And also for hydraulic pumps, usually driven by pump, we will use this formula. This efficiency of motor will be equal to pump power applied to the pump by motor by uh, power input to the pump, pi by pm. So we will use this formula. So at last we will use this total power output p naught is equal to specific weight times q times hp total head loss. So we will use this all these formulas. So let us begin question number 1, which is problem 4.5.4. Here, question asks about water hammer in concrete pipeline. So the mining operation, diameter is diameter is 2 feet, and the length of pipeline is 1,000 feet long. So here all the unit is given in feet, so we need to take care about that. So before I begin solving the problems, so I will explain what is water hammer. The water hammer occurs when a sudden change in flow rate, like an instantaneous valve closure, that creates a pressure wave in the pipe. The kinetic energy of moving water column must go somewhere, and it converts to a pressure surge. So let's define, here the question asks us to determine the pressure head rise in the feet of water if valve is closed instantaneously. So there is already given the condition valve were closed instantaneously. So for rapid valve, previously also I explained about formula. So this ΔH change in pressure head will be equal to initial velocity times C by G, where C is equal to EC by rho. So we have this formula for computing composite modulus. And for rigid pipe, so this whole term will be equal to 0 here. And so therefore, composite elasticity of EC will be equal to EV. So first step, since we know this EC now, we know the density of pipe, density of water. So we will use that here. C will be equal to 48, 70 feet per second. So when we compute this, so don't forget about this density is 1.94 slug per feet cube square. So here I just change the uh, uh, lb per inch square to lb per feet square. So don't forget about multiplying the elasticity by 144. So now we will calculate the initial velocity of initial velocity. So initial velocity will be like we will use continuity equation. So that gives, we know area, since diameter of pipe is given as 1 foot, so pi d square, and this gives us initial velocity of 3.8 3.18 feet per second. So now we will calculate pressure head rise del H. So since we know the formula, like del H is equal to B naught times C by G. We know we have all the value for B naught as well, C naught, and G as well. So this is for uh, is acceleration due to gravity in English unit. So it's like all the value are given. So we will just compute the del H pressure head rise. So that will be equal to 481 feet. So now the another question, the question asked was slurry effect, which is conceptual question. So if the water is replaced by a slurry with a specific gravity of 1.2, the density is higher. So looking at C like this one, looking at C, when density is higher, then value of C will be lower. So that will lower the del H. So that will lower the del H here. So pressure head rise would be lower for the slurry than for plain water. Intuitively, the heavier fluid moves more slowly as a wave. So this gives us we solved the question number 1. So we are done with conceptual question as well. We calculated the pressure head as well. So now let us move to question number 2, which is 5.1.2. That asks us to determine the flow rate of a water pump that overcomes an energy rate of 65 feet, and there is given of 750 kilowatt motor power of 750 kilowatt, and which drives the pump at an efficiency of 77%, and pump operates with an efficiency of 85%. So here there is some given conversion unit which we will use. So first we will write what are given, like from the question, uh, power of motor PM is also given, efficiency of motor is also given, and power of pump uh, is not given, but like there is given of efficiency of pump is given, and HP is 65 feet. That means here and energy is 65 feet, that is given. So let us draw like power cascade. So motor pipe will give to motor power will give pump input, and pump input will give pump output, that will give like fluid. So power is lost at each stage due to efficiency. We need to chain to efficiency together. First, motor converts electrical energy to shaft energy. Then the pump converts shaft power to hydraulic power in the fluid. So first, we will go through conversion of motor power and apply motor efficiency. So here, a power of motor PM will be equal to 750 times, it's just for conversion unit. So here there is given 1 kilowatt is equal to 1.34. So I just use that to convert that into horsepower. And so therefore power of input will be equal to P input is equal to so this one, like efficiency of motor times power of motor. So that will give us this efficiency is also given, EM is 77%, and PM power of motor is given, so we will have 774 HP. And now again, in this second step, we will apply EP to get output power. So P output is equal to EP times PI. So we have computed PI in earlier steps, so we will use that, and we will have our final power output as 3.62 times 10 to the power 5 feet lb per second. So here we need to convert like hp to uh, feet lb per second, so we multiply this. I think we are given this as well. 1 hp is 550 feet lb per second. So we got like power output as well. So we will just need to compute the uh, P naught power output, so which is given by specific weight times flow rate times HP. So our P naught is we are given, we just computed 3.62 times 10 to the power 5 as power output. So our main intention is to find Q. We know this as well, and HP, which is 65 feet. So based on that, when we do calculation, we will get the value for flow rate as 89.4 feet cube per second. I think there will be, you might feel confusion about the unit conversion, so you need to take care about unit conversion. So other than that, it's just applying the formula and just computing the value for flow rate. So now let us jump into question number 3. So question number 3 asks about, and I will first read the question. Like an earth dam is danger of following. Pump is needed to drain the small lake behind dam. The total energy head required to move water over the top of dam is like this 2.43 meter, and there is just available of just one pump which is 10, which has 10 centimeters diameter propeller pump, and that power requirement for that pump is 1000 watt, whereas combined pump motor efficiency is zero point 0.5, which is 50%. So we need to estimate the drawdown, that is how many centimeters the leg can go down in the period of 2 hours. Just understand, here we combine pump power analysis with simple volume balance. The pump removes volume of water over time, and we convert that to a depth change using the lake surface area. So here the lake surface area is also given. So first we are, I would write what we are given. We are given power of pump, that is 1000 watt, and efficiency of pump motor is given as 50%, and total energy head is also given, that is 2.43. So our main aim is to find the length, uh, how much it can go down. So first we need to find the pump output, that is P naught. So here like P naught will be equal to PM power of motor times E, efficiency of a pump motor. So that give us this 500 watt, so which is basically 500 newton per meter per second. And now next step, like since we already know P naught, so we will use to find the flow rate. So for flow rate we know this formula, like P naught is equal to specific weight times hp times q. HP is also given, rho is also given, peanut is also given. So we will just need to compute this Q. So which will give us Q as 0.021 meter cube per second. So this rho is 9790 Newton per meter cube square, and this HP is 2.43 meter. And so let us find the drawdown using the volume and given area. So, and we need to take care about time as well. So because the time is given as 2 hours, the drawdown will be equal to flow rate times time, that give us volume, and when we divide by area, we can get the value for drawdown. So what we did, we computed the flow rate earlier, so that gave us 0.021, and this time is 2 hours, so converting that into seconds, so we get 7200, and when we divide by given area, that is 5000 meter square, so we get 0.030 meter, so which give us 3.2 centimeter. So here, like one of the thing uh, you should be aware about is you shouldn't forget about converting hours to second, and do not confuse with specific of water in SI, and also do not confuse with the density as well. So now let us go through question number 4. So question number 4, it asks about computing the power requirement for pump to drive the pump installed in pipeline that moves. This is flow rate from reservoir A to a reservoir B. So the length of pipe is 100 meters, and diameter of this pipe is 0.8 meter, and it is made of rough concrete. So, and the head is also given like 20 meter, and pump efficiency is 80%, whereas motor efficiency is 74%. So this problem requires us to first find how much energy the pump needs to add HP, accounting for elevation and friction losses, and then work backward to find the motor power. We will use the energy equation first between the two reservoir surface, and we will need to use Moody chart to find the frictional factor. So we have drawn this reservoir A and B system. So I just write here power of motor which we need to find, and if power of efficiency, pump efficiency is also given, motor efficiency is also given, and for surface roughness, E is equal to 0.6 mm, which is for rough concrete. So let us use energy equation for relating the head loss and HP. So HA plus HP, head loss due to pump, and which will be equal to HB plus HL. This is head loss due to major plus minor head loss. So HP will be equal to HB minus HA. We just computed here, which is 20 meter, and HL. So HL is equal to, I earlier said that major head loss plus minor head loss. So for minor head loss, we need to consider when water enters and when water exit. So basically, this is value of K, E entrance will be equal to 0.5 and exit will be equal to 1. And for HF, this is from Darcy Weisbach equation. So this is frictional factor. We need to compute that. And L is given, D is also given, B we need to define, and we know G as well. So so we can calculate velocity and Reynolds number here, because F is unknown, B is unknown. So since we are given Q, design Q here, 2.05 meter cube per second, so we can calculate the V. So V gives us 4.08 meter per second. So since like I already talked about this E for computing the surface roughness coefficient, so E by D will be equal to 0.6 by 800 millimeter. So that gives us 0.0075 for rough concrete. And for Reynolds number, we just use diameter times velocity. Velocity is obtained from above by relating velocity, by relating flow rate and area. And this is kinetic viscosity. For kinetic viscosity of water at 20 degrees Celsius is 1 into 10 to the power minus 6. So that give us 3.26 into 10 to the power 6. So by relating this surface roughness coefficient and Reynolds number uh, and using the Moody chart, we get F is equal to 0.0185. Now let us compute HP. So HP will be equal to 20 plus HL. So HL will be equal to, since I think here we have talk about HP. So we will just put value of F, value of G, and we will have HL. So that give us 3.23. So HP will be equal to 23.2 meters. Now, finally, let us compute the pump output. So, which will be given as specific weight times HP times Q. Q is given, HP is given, rho is given. So that gives us pump output power is equal to 465.6 kilowatt. Now work back to motor power. So PM pump power of our pump will be equal to power pump output power by efficiency, this E, because it will be combined. So we need to multiply efficiency of motor and pipe. So pump. So that give us pump motor power will be equal to 787 kilowatt. So this sums of our homework. This sums our recitation class. So before concluding this session, I would like to say about, like, you need to take care about wave is celerity in water hammer equation. You need to take care about whether it is rapid surge or mild surge as well, and you need to take care about unit conversion. And so it's basically playing with the equation and finding the value. Thank you.